In second order differential equations, we find a series solution method or Frobenius method to find out solution of a second order differential equations. But in order to apply the Frobenius method or power series solution, the point about which we are expanding should be an ordinary point or at least a regular singular point. Fuches theorem is related to these conditions. So, in order to get at least one power series solution to a linear second order differential equation, the point about which we are expanding should be an ordinary point or at least a regular singular point. This is known as Fuches theorem. There is no guarantee that the power series solution or Frobenius method yield a second or two independent solutions to linear second order differential equations. So in order to get a second solution, we have to adopt another method. Before entering into the second solutions, let us discuss about symmetry of solutions. For example, a function, if y1 of function or a solution y1 of x, when we replace x by minus x, if y1 of x is equal to y1 of minus x, if after changing the sign of x into minus x, if there is no change in sign of the function, we can call that function as a even symmetric function. So if y1 of x is equal to y1 of minus x, y1 of x is an even symmetric function. So what is an odd symmetric function or odd parity function? If a function y2 of x is equal to minus y2 of minus x, if we replace x by minus x, if the function changes its sign, we can call that function as a odd symmetric function or a function with odd parity. The general form of ordinary differential equation is L of x, y of x is equal to 0. So L is a differential operator. In the case of a second order equations, L is d square by dx square plus p of x d by dy plus q of x. It is the form of that L of x in general. Or L of x is called a differential operator. So L of x y is equal to 0. If we replace x by minus x in the equation or in the operator, if L of x is equal to L of minus x, this operator have an even parity. So it is called an even parity operator. If L of x is equal to minus L of minus x, it has an odd parity. So it is an odd parity operator. If L of x does not satisfy these two conditions, that means the differential operator haven't any definite parity. It is called a function which have no definite parity. For example, if y of x is equal to x e raised to x square, it is the function. If you replace x by minus x, y of minus x is equal to minus x e raised to minus x square. This will become positive. So the equation is minus x e raised to x square. It is nothing but y of x. So it is nothing but minus y of x. So this is y of x. When we replace x by minus x, its value become minus y of x. So this operator or this function is a odd parity function. Whenever the differential operator has a specific parity or symmetry, either even or odd, we can exchange plus x and minus x. So plus or minus L of x into y of minus x is equal to 0. This plus 1 is for if L is even and minus 1 if L is odd. If y of x is a solution, then y of minus x is also solution if L has a definite parity. So in general, the solution or function y of x can be written as half y of x plus y of minus x plus half y of x minus y of minus x. So this is an even solution, this is an odd solution. So if it has an even or odd parity, we can resolve the solution into an even part and an odd part. If the solution have a definite parity, even or odd parity, we can resolve into two parts. The function can be resolved into two parts, that is an even part and an odd part. So let us consider some example. Parity check of Bessel function. We know that Bessel function is x square d square y by dx square plus x dy by dx plus x square minus n square y is equal to 0. So when we replace x by minus x, here L of x, this operator can be written in this form. L of x is equal to x square d square by dx square plus x d by dx plus x square minus n square. So when we replace x by minus x, if we do like that, we will get a solution like this. So L of minus x is equal to L of x. That means a Bessel function have a definite parity, and that parity is even parity because L of minus x is equal to L of x. So it can be split up into an odd part and an even part. So in the case of legendary equation, it is 1 minus x square d square y by dx square minus 2x dy by dx plus L into L plus 1 y is equal to 0. In order to check whether this function or operator is an even parity operator or odd parity operator, let us replace x by minus x. So you will get 1 minus x square. So this will become x square become plus x square itself. D square by dx square is preserved as such. So here there is a minus sign and here also there is a minus sign. Then it will become positive. So it is minus 2x d by dx plus L into L plus 1. So when we replace x by minus x, it will not change its symmetry or parity. So we call it as a even parity function. So in the case of a Legray operator, it is x y double dash plus 1 minus x y dash plus alpha y is equal to 0. So when we check this operator, we can find that it has neither an even parity nor odd parity, or this function has no symmetry at all. That about symmetry. Then let us come back into the conclusion of series solution method or Frobenius method. If we expanding about an ordinary or about a regular singularity, the series solution method or Frobenius method approach will yield at least one solution. So using Frobenius method or series solution method, using that we will get at least one solution. Whether we get one or two distinct solution depends on the root of initial equation. If the two roots of initial equation are equal, we get one solution by series substitution method or Frobenius method. If two roots are differ by a non-integer number, two independent solutions may be obtained. If two roots differ by an integer, then The larger of the two solutions will yield a solution. The smaller may or may not given a solution depending on the behavior of the coefficient. In the linear oscillator equation, we get two solutions, but for Bessel equation, we will get only one solution using this Frobenius method. So let us examine how we can find a second solution for the solution of ordinary differential equation. One solution for second order ordinary differential equation was developed by substituting power series solution or Frobenius method. In this section, we will develop two methods of obtaining a second independent solution, an integral method and a power series containing logarithmic term. So before entering into the second solution, let us examine what is meant by a linear independent solution and linear dependent solution. In general, a linear equations can be, let us consider the equation c1y1 plus c2y2 is equal to 0. If there is a relation, if any one of this c1 or c2 is not equal to 0, so there will be a relation. If c1 and c2 is not equal to 0, there will be a relation between y1 and y2. It means that they are dependent. y1 and y2 are dependent. y1 and y2 are independent only if c1 is equal to 0 and c2 is also equal to 0. If the solution y1 and y2 are linearly independent, for example c1y1 plus c2y2 is equal to 0, only when c1 is equal to c2 is equal to 0. Or in general, we can write sum over lambda, k lambda, phi lambda is equal to 0 is if phi lambdas are linearly independent. Phi lambdas are linearly independent only if all k lambdas are equal to 0 for all values of lambda. If a vector or a function are mutually orthogonal, then they are automatically linearly independent. A simple method to find a set of functions or solutions are linearly independent or dependent is to find out its Wronskian. So now we are going to find out whether a set of functions or solutions are linearly dependent or not. Suppose y1, y2, y3, etc. are set of functions or solutions. Then its Wronskian can be defined as this w is equal to Wronskian y1, y2, y3, etc. function. Its Wronskian can be written like this. W is known as Wronskian. So it is y1, y2, yn. If there are n functions or n solutions, we can write it is in the first row. And in the second row, its first differential is written in the second row. That is y1 dash, y2 dash up to yn dash. And when we proceed like this, and we have to stop it from the n minus 1th derivative. So last row will be y1 of n minus 1, y2 of n minus 1, yn of n minus 1. So the number of rows will depends upon the n value. It have n minus 1 rows. Okay, so this determinant is known as Wronskian. The first row is collection of functions, second row is first derivative, and third row is its second derivative, and last row is its n minus 1 derivative, and Wronskian is the determinant of this matrix. If Wronskian is a determinant, if W is not equal to 0, if the determinant of the matrix is not equal to 0, or Wronskian is not equal to 0, Wronskian is not equal to 0, it is a linearly independent functions. If Wronskian is equal to 0, it is linearly dependent. If the functions or the solutions are linearly dependent, then its Wronskian should be equal to 0. If they are independent, its Wronskian should not equal to 0. In the simplest case, c1y1 plus c2y2 is equal to 0. We have to differentiate. Here there are two functions or solution y1 and y2. So we have to differentiate it till 2 minus 1 or 1. First differential. We have to take its first differential. Okay. So it is c1 y1 dash plus c2 y2 dash is equal to 0. And we can write like this: y1 y2 y1 dash y2 dash c1 c2 is equal to 0. So if y1 and y2 are independent, c1 and c2 is equal to 0. That means its determinant y1 y2 y1 dash y2 dash should not equal to 0. This is known as the Wronskian. Let us consider an example. Y1 is equal to sin omega t, y2 is equal to cos omega t are two solutions. We have to check whether it is linearly independent or not. We have two functions, so we have to differentiate. In the first row, we have to write these two functions, and then we have to differentiate only once because it has two functions. So 2 minus 1, first differential. We have to take the first differential in the second row. So sin omega t, when we differentiate sin omega t, we will get omega cos omega t. When we differentiate cos omega t minus omega sin omega t. So when we take the determinant, we will get minus omega sin square omega t minus omega cos square omega t. Omega is a common factor, we can take outside, minus omega into sin square omega t plus cos square omega t. That is equal to minus omega not equal to 0. So it is a linearly independent function, so linearly independent solution. We know that sin omega t and cos omega t are linearly independent. We cannot one function from the another function. So this both by multiplying something or that we will not get the second function. So it is two linearly independent solution. So this way we can find out whether the function is linearly dependent or solution is linearly dependent or independent. Another example, e raised to x and e raised to minus x. We have to write e raised to x, e raised to minus x, two functions, so we have to differentiate it one second. E raised to x minus e raised to minus x is differentiating minus e raised to minus x. So it is minus x e raised to minus x minus of e raised to x e raised to minus x. So it is minus 1 into minus 1, it is minus 2, it is not equal to 0. That means it is linearly independent. So we can generalize this into this. Suppose we have n function, lambda is equal to 1 to n, k lambda, phi lambda is equal to 0. It is linearly independent when these phi's are linearly independent. If the Wronskian W is given by phi 1, phi 2, etc. Phi n, phi 1 dash, phi 2 dash, etc. Phi n dash, it have to differentiate till n minus 1. Okay, so phi 1 of n minus 1 until phi n of n minus 1, and we take its determinant. So if it is not equal to 0, then this phi lambdas are linearly independent. So how can we find a second solution? We know that y double dash plus p of x y dash plus q of x y is equal to 0. y1 and y2 are two independent solutions. Then w can be written as y1, y2, y1 dash, y2 dash, and its Wronskian is w is equal to y1, y2 dash minus y2, y1 dash. Here y2 is second solution of equation 1. So if we assume that we will get y1 from series solution method or Frobenius method, and we have to calculate the y2. So from equation 1 we will get y2 double dash. This equation is y1 and y2 are equally satisfied this equation. We can write y1 double dash plus p of x y1 dash plus q of x y1 is equal to 0. Equally y2 double dash plus p of x y2 dash plus q of x y2 is also equal to 0. So this is y2 double dash plus p of x y2 dash plus q of x y2 is equal to 0. From this we will get y2 double dash is equal to minus p of x y2 dash minus q of x y2. We will take this term into the right hand side, then we will get this. And now we are going to substitute for this y2 dash from this equation. So we know that w is equal to y1 y2 dash plus minus y1 dash y2. So this can be written as, so first we differentiate w Wronskian. We have to differentiate Wronskian. So w dash is equal to there are two functions. First one function take as a constant and differentiate the second. We will get y1. When we differentiate the first term, we will get two terms, and when we differentiate the second term, we also get two terms. So it is y1 y2 double dash plus y1 dash y2 dash minus y1 double dash y2 minus y1 dash y2 dash. So this term will cancel y1 dash y2 dash. This is y1 dash y2 dash, and you will get y1 y2 double dash minus y1 double dash y2. Next we will substitute for y2 double dash and y1 double dash from the above equation. So w dash is given by y1 is here, y2 dash is nothing but minus p of x y2 dash minus q of x y2, and y2 here, what is y1 dash, we replace y1 here, you will get y1 double dash, it is nothing but minus p of x y1 dash minus q of x y1. When we remove the bracket, this term y1 y2 minus q of x is here. Here also minus of minus plus y2 y1 q of x is here also. That two terms will cancel, and we can take minus p of x outside the bracket, and we can combine this first term and the third term. This second term and fourth term will cancel. So w dash is given by minus p of x y1, here it's only y1 y2 dash minus y1 dash y2. So it can be written as w dash is equal to minus p of x. This is nothing but Wronskian w. So if w dash is equal to 0, if the derivative of Wronskian is equal to 0, you can write w as a constant, because if its derivative equal to 0, that quantity becomes constant. So if w dash is equal to 0, w that is given by y1 y2 dash minus y1 dash y2 is a constant term. So from this equation number 4, we can write what is w dash is equal to dw by dx1. Okay, so that is given by p of x into w, or you can write p of x1. Okay, so minus p of x w. So dw by dw, we can take w here, common terms in single side. So dw by w is equal to minus p of x dx1. So integrating from x1 is equal to a to x1 is equal to x. This is an arbitrary limit. We are integrating the function x1 plus from a to x. We will get ln. When we integrate this, you will get a logarithm, natural logarithm. So ln wx by w of a. When we apply the upper limit and lower limit, w of x divided by w of a is given by minus integral a to x p of x dx1. Or from this we can write w of x is equal to w of a into e raised to minus integral 0 to x p of x dx1. Or when we take power on both sides, w of x by w of a is given by e raised to minus integral a to x p of x dx1, or w of x is equal to w of a e raised to minus integral p of x dx1. And we know that the Wronskian w of x is given by w1 y2 dash minus w1 dash y2. Or when we differentiate d by dx of, now we are going to write another equation for this. Okay, for obtaining that, we are going to differentiate d by dx of y2 by y1. What is the d by dx of y2 by y1? And it is given by d by dx of y2 is by y1 means y1 raised to minus 1. So when we differentiate this, we will get y1 dash taken as constant. So y1 dash y2 dash, here there is no negative side, it is y2 dash. When we differentiate y1 raised to minus 1, you will get minus 1 divided by y1 square. Y2 remains as such, y2, and it's after differentiation you will get y1 dash. It is d by dx of y1 dash is nothing but y1 dash divided by minus of y1 dash divided by y1 square, and it is nothing but y2 dash divided by y1. It is nothing but y1 dash divided by y1 square. We take y1 square outside, y1 square, so we have to multiply with y1. So you will get y2 dash y1 minus y1 dash y2. It is nothing but the Wronskian. So when we take y1 dash square into this equation, you will get, or from this equation, what is y2 dash y1, sorry, y2 dash y1 minus y1 dash y2. Here we have to write 1. Okay, so that is given by y1 square. Y1 square will taken into the left hand side. So y1 square into d by dx of y2 by y1. So now we are going to write instead of y1 y2 dash minus y1 dash y2, we are going to write y2 dash y minus y1 dash y2. So the Wronskian become y1 square into d by dx of y2 by y1. So from the above solution, we already we already derived this equation, that is w of x is equal to w of a into e raised to integral p of x dx. Okay, it is from here w of x is equal to w of a e raised to minus integral 0 to x p of x dx. Instead of w of x we can write, so instead of w of x we can write, it is y1 dash d by dx of y2 by y1. So d by dx of y2 by y1 can be written as w of a e raised to minus integral p of x dx divided by y1 square. Okay, integrating from we are going to integrate for x2 here. This is first one integration for x1. Now we are going to integrate for x2 from the limit, lower limit, arbitrary limit b to x. So when we do like this, you will get y2 is equal to y1 into w of a. Here this is total, w of a is a constant, so we can take outside. Then total integral b to x e raised to minus term is here, e raised to minus integral 0 to x p of x dx1 divided by y1 square into dx2. Or in general, when we take w of a, when the Wronskian or determinant is equal to 1, the solution will become y2 of x is equal to y1 of x into b to x e raised to integral p of x dx1 divided by y1 square into dx2. So we can omit the arbitrary lower limit, and if y1 of x we already get one solution, then from this equation you will get the second solution by doing this integration. In a special case, in certain case, if p of x is equal to 0, in special case when p of x is equal to 0, we will get this equation as, we can rewrite this equation for y2 as y2 of x is equal to y1 of x integral, when this is equal to 0, this term vanishes, dx2 divided by y1 square. Okay, that is, from the above equation, if one solution is known, by integrating we can generate the second solution. One example for is that a second solution of a linear oscillator. We already know that one solution for this is sin theta, another solution is cos theta. Here in this example we take one solution as sin theta, and using this formula we are going to find out the second independent solution. Okay, for that we get, this is the equation. Here omega is taken as 1 harmonic oscillator. So this equation, a simple equation, will become a simple equation, that is d square y by dx square plus y is equal to 0 with p of x is equal to 0. Here when the p of x is equal to 0, that differential equation is reduced to this form. So one solution, we assume that one solution y1 is equal to sin x, omega t, omega is equal to 1, so it is sin x. So this equation for second solution, if p of x is equal to 0, y2 of x is equal to, the general solution for y2 x is x when p is equal to 0 is y2 of x is equal to y1 of x integral 0 to x dx2 divided by y1 square, it is nothing but sin square x2. So when we integrate this dx2 divided by sin square x2, you will get minus cot x sin x into minus cot x. It is nothing but sin x minus cos x by sin x. This sin x and sin x cancel, so minus cos x. So clearly we get the second independent solution. So this way, using these solutions, we can find out the second solution for linear differential equation. First solution we can find out from Frobenius method or series solution method, and so we can find out the second solution using this method. Thank you.